ever wonder what really makes your phone, your computer, basically every digital device you own actually work? Well, it all comes down to one tiny, revolutionary component. Billions, and I mean billions of them, are in the device you're watching this on right now. It's called the MOSFET, and it's the absolute foundation of our modern world. So today, let's break down how this tiny digital faucet works. So why is it everywhere? Simple. It's incredibly versatile. Get this. The exact same device can be used to precisely amplify a really weak signal, like the one from your Wi-Fi antenna, or it can act as a simple lightning-fast on-off switch. This dual personality, being both an amplifier and a switch, is what makes the MOSFET the ultimate electronic building block. Okay, so how on earth can one little thing do so much? Well, to really get a gut feeling for it, we need a simple but really powerful analogy, one we're going to keep coming back to. I want you to think of a MOSFET as a faucet, but instead of controlling the flow of water, it controls the flow of electrons. All right, so if we're calling it an electron faucet, let's pop the hood and see how it's built. To understand how it all works, we first need to figure out how we actually turn the handle. Okay, so a MOSFET basically has 4 connection points, or what we call terminals. You've got the source, which is where the electron current comes from, and the drain, which is where it flows to. The body is the silicon foundation it's all built on. You can think of that as the pipe itself. But the most important part, the real star of the show, is the gate. This is the handle of our faucet. And here's the crucial part. It's totally insulated, meaning it controls the flow using an electric field without ever actually touching the electrons themselves. It's kind of like magic. Now, think about a real faucet. You can't just breathe on the handle and get water, right? You have to turn it past a certain point to get it to kick in. Well, for a MOSFET, we call that point the threshold voltage. It's the absolute minimum voltage you need to apply to the gate just to start creating a path or a channel for electrons to flow. If you don't hit that voltage, nothing happens. The faucet is completely, totally off. So you've passed that threshold voltage and the faucet is on. How do you control how much current flows? That's the job of the overdrive voltage. And it's exactly what it sounds like. It's how much extra voltage you apply over that initial threshold. The more you crank the handle past that starting point, the higher your overdrive voltage, the wider the faucet opens, and the stronger the flow of electrons becomes. This is what gives us that really precise control. Okay, now this is where things get really cool. Depending on the voltages you put on it, this one single device can act in 3 completely different ways. It can be off, it can act like a resistor you can tune with a voltage, or, get this, it can be a perfect constant source of current. How is that even possible? All right, let's break it down with this table. First up, cutoff. Super simple. The gate voltage is too low. Below the threshold, the faucet is off. Period. No channel, no current. That's your digital 0. Next, we open the faucet just a bit. We're in what's called the triode region. Now, the flow depends on 2 things: how much you've turned the handle and the electrical pressure at the drain. It acts like a resistor you can control with a voltage, which makes it the perfect digital on switch, your 1. And finally, what happens if you crank the handle wide open? You hit saturation. At this point, the flow is just maxed out. You're getting a constant, steady stream of current. It's like a fully open fire hose. And that predictable, stable flow, that's the secret sauce for building amplifiers. And believe it or not, there's a beautiful piece of physics that describes that saturation mode. It's governed by the famous square law. This equation tells us that the drain current is proportional to the square of the overdrive voltage. So what does that mean in plain English? It means a tiny little nudge on the gate voltage creates a much, much bigger change in the output current. That's amplification, right there in the math. This is a fundamental equation engineers live by when they're designing analog circuits. Okay, so we have this core equation. How does an engineer actually take that and design a circuit to get the exact current they want? Well, they have a whole toolkit of parameters they can play with to control the flow. An engineer has a few knobs they can turn. Now, some things are just baked into the manufacturing process. You can't change those. But the main tool a circuit designer has is the physical shape of the device itself, its aspect ratio. By controlling the ratio of the channel's width to its length, right there on the silicon, they can basically set the size of the pipe. You want more current? You design a wider, shorter pipe. Want to restrict it? Make it narrower and longer. This is the primary way they dial in the performance of a transistor. Of course, the real world is never quite that perfect. We said the current in saturation is constant, but, well, that's not entirely true. There's a real-world effect called channel length modulation, which basically means the current actually creeps up just a little bit as the drain voltage increases. So, sticking with our analogy, you can think of it as a tiny little leak in our faucet system. It's one of those small imperfections engineers always have to keep in mind, especially for super precise amplifiers. A single faucet is useful, sure, but the real magic, the real power, comes when you combine them by the billions. And to do that efficiently, our standard MOSFET, the NMOS, needs a partner, a perfect opposite. And here it is. Meet the P-channel MOSFET, or PMOS for short. It's the perfect yin to the NMOS's yang. Where the NMOS uses negative electrons to carry current, the PMOS uses positive charge carriers called holes. You can just think of them as bubbles flowing the other way. So, the result is an NMOS turns on with a positive voltage, but a PMOS turns on with a negative one. In our analogy, if the NMOS faucet opens when you push the handle, the PMOS faucet opens when you pull it. So what happens when you put these two push-pull devices together on the same tiny piece of silicone? You get CMOS, that stands for complementary MOS. And this is everything. It's the technology behind practically every modern digital chip. Why is it so great? Because when you pair them up, you can build circuits where one of them is always off. This means they use an incredibly tiny amount of power when they're just sitting there, not switching. It's this insane energy efficiency that made things like your smartphone powerful and portable, even possible. And really, that's the whole incredible story, isn't it? We started with this super simple idea, a single faucet controlling electrons. Then we gave it a perfect push-pull partner and figured out how to manufacture them not by the thousands or millions, but by the billions. And in doing so, we built the literal engine of our entire digital world. That is the unbelievable power of CMOS. So think about this. The next time you tap your phone screen or talk to a smart assistant, just remember what's really happening. Billions of these tiny, invisible electronic faucets are turning on and off, all in perfect sync. And this fundamental building block? It just keeps getting smaller, faster, and more efficient year after year. So the real question is, as we start packing trillions of them onto the next generation of AI chips, what new realities will they enable next?